This question is a SUVAT equations question. We know that because it talks about constant acceleration at the very beginning. So we know we can apply any of the 5 SUVAT equations from the formula book. However, it's not a standard question of the straightforward type you might get near the beginning of the chapter, because they're not just giving you 3 values and asking you to calculate a 4th or a 5th. They're giving you a couple of clues, and you're supposed to combine more than one SUVAT equation together to solve and find the unknown values. So we've got 3 points, A, B, and C. AB is 22 meters apart, B and C are 104 meters apart. The car travels between A and B, taking 2 seconds to do so, and then it takes 4 seconds to travel between B and C. For starters, you can try to visualize the situation. I always think about telling the story or getting the narrative behind it, and often a large part of that is making sure you've got a nice clear diagram. It doesn't have to be to scale. You'll notice on this one, it's not obvious that B and C are much further apart than A and B, but it's good enough for me to get a sense that they are further apart. If you want to look in a bit more detail or make some quick estimates, then notice that BC at about 100 meters is nearly 5 times as far apart as A and B, which is only about 20 meters. But if the journey is done in only twice the time instead of 5 times the time, it makes sense that the car would be accelerating, in other words, speeding up as it goes along the journey. Now we've got some information, so I'm going to start putting my information on the diagram so I don't need to keep going back to the text to identify the bits that I need. The distances for a start between A and B and between B and C, and then the time taken to travel. And that seems like all we've been given, 2 bits of information for 1 bit of the journey and 2 bits for another part. But there's another crucial element to this, and that's the fact that the acceleration between A and B is the same as the acceleration between B and C. And because B is just a checkpoint along the way, the speed as the car passes through B is the same. It's basically the same car traveling at its own speed. But what that means is the final speed in the AB section is equal to the initial speed for the BC section. So we can add a bit more information on here. We can say, for instance, that if we call the initial speed of the car U, then we can use V perhaps for the speed at point B, and I know W for the speed at C. And encoding it like this and deciding to use the letter A to represent acceleration throughout effectively tells the equations that the acceleration is the same in AB as it is in BC, and that's going to be crucial for solving this one. The next thing we should think about before we go any further is what the question is asking us. So the 2 main questions that go through my head whenever I'm doing a problem solving process is, what do I know and what do I need? Now I've encoded on the screen pretty much all the information I have, everything that I know. The next thing to jot down is what I need, what I'm looking for. And the question spells it out for us. We're looking for the speed of the car as it passes through the point A, and we're looking for the acceleration. And this is helpful for me because otherwise I'm looking at the problem and I'm thinking, I've got U, V, W, A, that's 4 different unknowns. And that's a lot to work with, and I might end up with all sorts of weird and wonderful simultaneous equations. If I can narrow my focus down to creating equations involving U and A, is going to be beneficial. And equations that involve V or W, I can either avoid generating in the first place, or if I'm forced to, can I find other equations that will let me link those to U and A? Perhaps I can do a substitution to eliminate those variables from my equations and generate new equations in the variables that I am interested in. And if you think about it from a pure maths point of view, if you've got 2 unknown values that you need to find, you're going to need at least 2 equations to tell you about those things. That's simultaneous equations. 2 unknowns will require 2 equations in order to uniquely identify the 2 points. So let's start by doing the next logical thing with SUVAT equations. Consider a particular phase of motion and work out values for S, U, V, A, and T. Now there's a few obvious phases of motion we could choose here. We could look at the journey from A to B, or we could look at the journey from B to C. Alternatively, we could take the more holistic view and look at the entire journey from A all the way through to C. And any and all of those are valid, and they each have some different advantages and disadvantages. In each case, the only known values are the displacement and the time, and everything else is unknown. But crucially, they're all connected to each other. So let's start with A to B. It would be possible to create an equation that used S, because we know S, that makes sense, and it uses T, because we know T. And then I suppose we want one that involves U and A, but not V, if we can avoid it at this stage. because I'm trying to create some information that tells me about u and a. So the logical choice here would be s equals ut plus half at squared. So you can give that a try, creating an equation from a to b. And while you're at it, you could do a similar thing for the a to c scenario, and then have a go at b to c and see why that's a bit different. And you might already be able to see a solution route that only uses those first two that I've already put up in boxes, but it's useful to look at the B to C as well to see how that might work out as well. Try pausing the video and giving that a go, and then you can come back and see what the next bit might look like. So the B to C journey is a little weirder, because if you try using s equals ut plus half at squared, you're not going to get an equation directly that links u and a, because u doesn't appear in that list. But the initial speed for B to C is v, and v is connected to u and a if you go back to the a to b scenario. So because v equals u plus at, we can write capital V as capital U plus 2 times a. And that allows you to then go back and substitute in and finally create for yourself the equation we're looking for. If you've already managed to set up the s equals ut plus half at squared equations for the other two sections, a to b and a to c, and if you've now done the b to c one, then you should be able to simplify those down to get something like this. 11 equals u plus a when we look at a to b, 21 equals u plus 3a looking from a to c, and finally, if we use the fact that v equals u plus 2a, we can sub that in and convert our last equation into 26 equals u plus 4a. Interestingly, these equations are all different. None of them are obviously just a combination of the other two, although if you mess around with them enough, you might be able to find a way to relate them. But it turns out they are all valid because we created them all from valid sections of the motion. So nothing is wrong about any of those three. It's just that we don't, strictly speaking, need all three of them. So any two of these would have done the job for you. I think it's useful sometimes to see all the different routes into a problem, and then next time you're dealing with a problem like this, you can be a little bit more discerning, if you like, in terms of what you choose to do. Finally, this is a quick visual just to illustrate the point that all three equations correspond to a consistent solution pair. There is a single value for u and a corresponding single value for a that satisfies not just two of these, but any two of these equations, because in fact, all the lines, if you drew them on a u versus a graph, would all cross in the same place. So solve them however you like. You could do it on the calculator, but these are nice enough that you can probably do it by hand. You can almost do it by eye with these equations. Elimination works quite well, and you should find that a speed of 6 and an acceleration of 5 works really well. You could then test that out, ask yourself just briefly whether the numbers make sense. If the speed is 6 at the beginning and you accelerate for 2 seconds at 5 meters per second, then you'll be going 10 meters per second faster than you were. You started at 6, you're now going 16. That gives you an average speed of halfway between 6 and 16. Do 6, add 16, and then divide by 2. So what's that going to be? 22 divided by 2, 11. And if you're going at 11 meters per second for 2 seconds, you're going to cover a distance of 22 meters. So that's consistent with the first bit of the scenario. There are other ways to look at this problem. If you want to continue, the next slide is going to look briefly at what the velocity time graph scenario would look like. And you might find that's an easier way to visualize the whole thing. But it's worth knowing that when you're dealing with a situation like this, sometimes just applying SUVAT to a few different sections of the scenario and then doing some algebra is all it takes. The trick is to find the right algebra. So figure out which equation is going to give you the most useful thing and run with that. And finally, if you do want to look at this from a velocity time graph perspective, then that can be really helpful as well. The initial velocity doesn't actually make much difference to your diagram, and the acceleration doesn't either. It will affect how high up your line begins and the gradient you draw. But if we only put values on that we know, then the calculations we do will be valid anyway. So for instance, mark on the times that you're given, mark on the distances that you know, that will be the area under the graph, and then put on the initial velocity. Use the acceleration to calculate the velocity at each of the relevant points. From that perspective, now you've got everything you need, but it's on one diagram and it only involves u and a. So set up an equation involving the area of the green section, set up another equation for the area of the blue section. Once you simplify those, you'll be solving simultaneously in much the same way we've done before. You'll probably end up with a couple of the same equations, in fact, and then you'll have your solution.